Let us start by recalling some notions on dynamical system associated to substitution. So let's start by fixing an alphabet denoted by A with the symbols 1 to D, and consider also A plus the set of non-empty words on this alphabet A. A substitution, it's going to be a map from theta, a map theta from A to A plus, such that there exists some letter A in the alphabet having length at least 2. So I'm going to denote the length of the word theta A by these 2 bars. And by concatenation, we can extend the definition of the substitution to the set of words A star. So for example, for a word given by 2 letters AB, theta of AB is just the concatenation of the image of A by theta and the image of B by theta. So an example, which is going to be the main example for this presentation, is the Thue-Morse substitution. The alphabet we are going to consider is just the symbol 0 and 1. So theta of 0 is the word 0, 1, and the image of 1 is 1, 0. So since we can extend the definition of the substitution to finite words, we can iterate the substitution. So we start by the image of 0, 0, 1. The second iteration, we obtain this finite word 0, 1, 1, 0. And we can do this infinitely many times and obtain an infinite word, which I will denote theta infinity of 0. And I'm going to call this infinite word the Thue-Morse word. Note that this infinite word is a fixed point of the substitution, in the sense that if we apply the substitution to this infinite word, we're going to obtain the same word. Let's consider the next notions related to substitution. So the first notion, it's going to be the substitution matrix, which I will denote by m theta. So the ij component of this matrix is just going to be the number of symbols A that I found in the image of the letter J. So it's a matrix with positive integer entries, so or non-negative integer entries. And we are going to say that the substitution theta is primitive when this substitution matrix is a primitive matrix, in the sense that there exists some power of the matrix such that all entries are strictly positive. When, since we are always assuming that our substitutions are primitive, I can give a second notion about the substitution. When the substitution is aperiodic, that's going to be the case when this fixed point. So we can always assume there exists such a fixed point for some letter A that we iterate infinitely many times, such as just as in the case of the Thue-Morse word. If this fixed point is aperiodic, we're going to say that the substitution is aperiodic. Okay, so that's the main combinatorial object. And now for the dynamics, I'm going to define the phase space, which is going to be our subshift associated to a substitution. So we start with always a primitive aperiodic substitution, just for having a nice space. I'm going to define the set x theta as all the b infinite words on this alphabet A, such that every finite window or every finite cylinder appears as a subword of some iterate of the substitution on some letter. Okay. So there exists some A in the alphabet and some power such that all the finite words we can find in this B infinite words appears as a subword or on this iterate. And for the dynamics, we are going to consider just the left shift. So it's going to be denoted by this letter T. And we all we do is just shift one step to the left, the whole B infinite word. Please interrupt me at any time if there's you are needing any clarification on the definitions. So our first result, we can recall, it's a classic result for this space, for this dynamical system, is the next one. So there exists a unique Borel T invariant measure mu.
So excuse me, Juan, the bottom of your screen I cannot read, but maybe you will make it bigger later, yes?
Yeah, that's the way I'm doing it, sorry, yeah.
Oh, okay, perfect, okay, good. Mm-hmm.
So the theorem tells us that there exists a unique Borel T invariant measure for this space. In particular, the system is ergodic. And also another result is that this such a system is never mixing. Okay, so that leaves us with the case where we can study eigenvalues of this system, and also the case we could always have the case of weakly mixing, and we can study properties of the spectral measures such as singularity. Even we can find absolutely continuous component, but the fact that the system is never mixing tells us that the spectral measures cannot be all absolutely continuous with respect to Lebesgue measure. So that we are going to study the continuous spectrum, and we are going to base our analysis in the next cocycle that I'm going to define. So that's the next section. So this is called the spectral cocycle, defined by Alexander Buffetov and Boris Solomiak. So I'm going to define it in the most general case, which is for suspensions over S-adic systems. But sorry, in this case, I'm only going to define for one substitution. So don't worry. But we are going to consider the suspension for the moment. So I'm going to consider this parameter S in the d-dimensional torus, but I'm going to decompose it in this way. So omega is going to be our spectral parameter later. And we're going to consider some positive vector P. So how do we how do we define this cocycle to a substitution? So we start with some substitution theta. We consider the image of some letter A. So it's going to be W1 till WKA. And the first matrix of our spectral cocycle will be the next sum of complex exponential. So this notation E, it's given here, it's just the complex exponential. And we are going, so the entry AB, we are going just to sum the number of B in the same way as we did for the substitution matrix, but instead of only adding the number of times that appear each letter, we are going to codify that with this complex exponential. So we are taking the parameters of the coordinates of our vector S, and we are summing all the appearances, all the prefixes of appearances of the letter B in the word given by theta of A. Okay, here delta, of course, is the delta Kroneker's delta. And for the rest of the cocycle, we are going to consider the dynamics given by the endomorphism obtained from the substitution matrix. In fact, from the transpose of the substitution matrix. So given here. Okay, so that's kind of a heavy definition. So maybe with an example, it's much easier. So let's consider the next substitution. Just for notation, we are going to put zj, the complex exponential associated to the parameter sj, and consider the next substitution, theta on 3 letters. So, for example, we can check the entry to 2 of this matrix. So what we have to do is look at all the appearances of 2 in the image of theta of 2. So since the first letter is a 2, we have to take the prefix before that, so we have an empty word, and we put the exponential with no parameters, and that will be the number 1. And then, since in the second position we have also a 2, we add to this 1, we add the prefix, which in this case is only this 2 over here, and we put the parameter theta 2 over here. And this sum of complex exponentials give us the entry of the matrix. Is it clear, the definition? So we can continue if there's no questions about that. For us, actually, since I said this cocycle is defined for in a more general case for suspensions over subshift. For our case, we are going only considering the case where P in the decomposition of S it's the vector 1, 1. Well, in the case of the Thue-Morse in the Thue-Morse substitution, since we have 2 letters, we only have to consider 1, 1. Otherwise, we will have to consider the vector with d1s as entries. So for the Thue-Morse substitution, what do we have? We have the next expression for the cocycle. So you can see we have the first cocycle, since we have a 0 in the first, so we have obtained this 1 over here. And since we have this 1 over here, we obtain this complex exponential with parameter omega. Okay. And continuing with the definition, we obtain this expression for the cocycle. And one thing we always study for multiplicative cocycles, it's the top Lyapunov exponent, whose definition I recall here. So the top Lyapunov exponent tell us the exponential growth of this multiplication of this matrix product. So it's defined by this letter T, and it's going to be the limb sup of 1 over n log of the cocycle at time n. And you can take, of course, any norm, since we are working in a finite dimensional space. So just for motivation, let me state one result that relates the spectral cocycle with a well-known number theory number theoretical problem, which is the lemma problem. So this is the theorem of Beck, Kunz, and Manivo that says that the lemma's problem for Borwe's polynomial, that it's to find the minimal Mahler measure for an integer polynomial. In the case when we restrict the problem for the class of Borwein polynomials, which are the polynomials we only have as coefficients 1, 0, and -1. So that's a Borwein polynomial. In that case, the lemma's problem is equivalent to the next question. If there is any C, positive C, such that the spectral cocycle, the top Lyapunov exponent of the spectral cocycle, it's bounded away from 0 by this constant C, and that holds for all primitive constant leg substitutions on 2 letters, and such that, we are considering only the case when this top Lyapunov exponent is in fact different from 0. As we are going to see, in fact, for the case of Thue-Morse, the top Lyapunov exponent is going to vanish. So that's not in this case. So this theorem is just for give some motivation for studying this spectral cocycle outside of the world of studying the spectrum of substitution dynamics. So what we are going to do first is to actually prove this thing that the top Lyapunov exponent is it vanish. So let us recall the definition of twisted Birkhoff sum. So we're going to consider these 2 sums. So in the first one, we are going to sum all the exponentials corresponding to the times we look at the letter 0 in this infinite word given by the Thue-Morse word. Okay, and we are going to stop at time 2 power n minus 1, since it's the n is the length of the n iteration of the Thue-Morse word. So to understand the top Lyapunov exponent, we have to understand the behavior, the growth of these 2 sums. So instead of consider them independently, we are going to consider them together. And you can see that the sum, it's really easy to understand. Since we only have 2 letters, we are going to sum every single exponential, and we have a bounded geometric sum, which is no issue. We have an explicit formula. What's next is to study the difference of these 2 sums xn and yn. For that, we are going to use some arithmetic characterization of the Thue-Morse word. So remember, the Thue-Morse word, it's always going to be denoted by this letter U. And the arithmetic characterization is the next one. So we are going to consider the sum of digit function given by this S2. So each integer k, we can decompose it in its base 2 form. So the coefficients are going to be this k0 till kn minus 1, and this function only sum all of these digits. And the arithmetic characterization of the Thue-Morse word tell us that the k letter of the Thue-Morse word is exactly S2 of k mod 2. How this help us? So I'm going to show you this small calculation. Sorry, maybe I'm going to. Yeah, that's better. So for the difference, what we have this, using this arithmetic characterization, we can write down the next sum for the difference. And I'm going to call this kind of sum, exponential sum, the Thue-Morse polynomials, denoted by Pn of omega. So writing down -1 as a complex exponential, like this, we can actually make the sum explicit. Instead of summing in the variable k, we're summing in its digits in base 2, and we arrive to the next risk product given here. So for understanding the growth of this difference, we take absolute value and we arrive to the next expression. And actually from here we can see that the top Lyapunov exponent vanishes just by application of the Birkhoff-Khinchin ergodic theorem, since we are going to have an ergodic transformation given by this 2 times map, and the function f of x equal to the log of 2 sine of pi x. It actually have integral equal to 0, so integral f dx it's equal to 0. Okay, so from here we can see that the matrix product we have first had a sub-exponential behavior. That means have a top Lyapunov exponent equal to 0. But we can actually prove is that we can give a better estimate, sharper estimate for the sub-exponential behavior. So this is the main result I want to show. There exists some constant b, universal, independent of omega, such that for almost all omega, there exists some time n0, such that from this time, the growth of the Thue-Morse polynomials, Pn, it's governed by this sub-exponential growth. And in fact, we can also say from this theorem that the Thue-Morse polynomials does not decrease exponentially fast also. So the proof it's based in the bounded law in the law of yeah.
Constant B depends on omega or not?
Sorry?
The question is, does the constant B depend on omega or not?
No, it does not depend on omega.
Okay. By the way, you have 2 minutes.
2 minutes left. Yeah.
Yep.
I'm just going to see the sketch of proof and we are done. So thank you. So the sketch of proof is the next one. It's really straightforward. If we don't mind the hypothesis, it will be the next thing. So we are going to take log to this product. And we are going to see these terms over here as random variables. And we would like to use the law of iterated logarithm. No, sorry. So since this, as I said, this random variable has expectation equals to 0, if they were independent, we could use the law of iterated logarithm to, well, in fact, our constant in that case will be equal to 1, but I write it down b. And the proof will be done. It will only be that. But unfortunately, of course, this is not the case since we have 2 problems. The random variables yj are not independent. But in that case, we can still do something since we have that the transformation given by this 2 times map it's mixing. But in that case, we can the classical setting is given by holder observables. But in our case, this function f that I write down here, it's not even bounded. So since I have maybe minus 30 seconds, I'm just going to state one last theorem that give us, we can get rid of these problems since we have this deep result. With that, I'm going to finish. That it's not a law of iterated logarithm, but a bounded law. Tell us basically that we can still have the inequality here. Instead of this equality, we will have an inequality for our setting. So the conclusion of the theorem, it's this bounded law of iterated logarithm, and with that we can conclude the result. So sorry for the delay, and thank you very much for your attention.
If anyone has any questions, please ask, and go ahead.
I always have the same question, which I think Juan already knows. So, but why Thue-Morse? Why not more general substitutions, even of constant length, if you want?
For the moment, it's just because of the for the arithmetic characterization. That's not.
But for constant length, Juan.
But constant, I don't think you for every constant length substitution you have such a.
Okay, but maybe this is debate. This is disagreement. We can discuss more privately.
I mean, I think you still you need some hypothesis like a billion constant length or something like that.
What do you mean a billion?
That the images are that the images have different at each position they have different letters.
Okay. This continues to surprise me. But
okay, so thank you very much. And let's say thanks to Juan for a very nice talk.